So now I'm going to be discussing the solution to my container loading problem. So I have used A star with beam search and first I'll state the problem. So the problem is to basically place the yard containers into ship stacks so earlier port containers are accessible and the ship also stays balanced. Now the algorithm that I'll be choosing is basically going to trade off between the travel distance required by the crane to load and unload the containers onto the ship, right, along with the future unloading cost and the left and right weight balance of the ship. And I basically, the goal is to minimize this objective function, which I will talk about in the later slides. So it's basically loading distance plus the expected rehandle cost, which is the number of inversions required in a stack, and the imbalance penalty. So I use basically a constructive A star style search with the beam pruning for basically getting the top k partial solutions, because it is simple and also has an admissible heuristic, right? So now moving on to the next slide. So basically the problem formulation slide. So basically I have used containers and stacks. These are basically two data classes that I have used. Uh, so the container has a unique container ID, its weight, and the destination port at which this specific container has to be dropped, and also the position in the yard that it is present at initially, right? So I've considered a 2D coordinate axis, right, x comma y, let us say, and basically the container could be present at any point, and that is the yard position. For example, let us say this is 2 comma 1. So at this position, container C1 is present, and the weight, let us say, is 25 tons for this container, right? 25 tons. And also, let us say the destination port is 3. Destination would be natural numbers up till the point n. N is basically the number of containers that we have chosen. And 1 is the earliest port to be dropped off, and n is the last port. Then I have the data class stacks, which basically is the stack position of which is the stack that is present on the ship. So let us say this is the ship, right? If this is the ship that we have basically vertical stacks present on the left and right sides of the ship, right? So we have stacks present in which the containers will go. So I have basically the name of the stack, the ID of the stack for its unique identification, and the side at which it is present. So let us say this is the ship that we have, right? For this ship, it has been basically divided into left and right portions. This is the left portion, and this is the right portion. So basically, the side to which this particular stack belongs, the ship position, that is on which position of the ship is this stack present. So on the ship also it has a coordinate axis. So we basically define the position at which the stack is present by ship position and the height limit of each stack. So each stack would have a height limit. That is beyond that height limit, we cannot place containers, right? And I've also basically for each stack I have slots. So these are basically ordered bottom to top, right, in which the containers will go. All these slots will be filled by the containers. So these are the two data classes that I've used. Also state is the current stack assignment of the containers, right? And our action is to place a container in a stack, right? So any container that is present outside, we have to place the container. Let us say this is the container that we have to place this container into the stack. That is the action event. And then the goal is for all containers to be placed while also minimizing the objective function, which I'll discuss in the fourth slide. Hard constraints that we have is firstly the capacity, that is the height limit. So that is a hard constraint, and basically capacity is enforced strictly, and we basically also have unique placement of our containers in a stack. Then the soft constraints we have, that is the penalties, the destination blocking or inversion in slot. Basically an inversion would be that any earlier port container is coming under a later port container. That is, any container which has to be dropped off first is coming below a container which is to be dropped off later, right? For example, if we have I comma I and j as these two containers, and the destination of I is less than destination of j, that means we have to drop off I first, then j would come. So that would obviously require us to remove all these containers and get to I first. So each inversion basically translates to a rehandling or basically removal of all the containers from the stack till we get the container I, which has to be dropped off at an earlier port, right? So these are the soft constraints, and we also have the balance penalty, which is basically the absolute difference between the left and right weights of the ship. And the total rehandle penalty inversion count we have already discussed. Now moving on to the next slide. So the assumptions being made. So basically, firstly, I am considering a discrete stack model. So each ship bay, that is the vertical compartment or space that can hold containers. So every ship has a bay. So the stack that I'm considering is basically called the ship stack, which is going to be a vertical component which can hold the containers, is represented as a vertical stack with a fixed height limit. So we have fixed height limit. For example, if we have 4 as a height limit, that means we can only fill 4 containers in one stack. But in reality, ships have bays of varying widths and sizes and other rules which have been ignored here for simplicity. So that is the assumption. Then second is the weight distribution. So the balance is modeled only using the total weight difference between left and right sides of the ship. That is delta W is equal to left weight minus right weight, right? And the absolute difference between them. So the assumption here is that longitudinal, that is front back balance, and torsion stresses are negligible compared to the left right imbalance. But in reality, in ships, the torsions do matter. Here we have ignored for simplicity. Next, we have the destination encoding. So each container has an integer destination where lower destination corresponds to an earlier port. So if the destination value is lower, that is, for example, if we have 1 or 2, that means the port would come earlier. And then if we have for example, we have destinations up till 20. So basically, up till 20, that is the last port, and we start our dropping off the containers from 1 and go till 20, right? So the constraint is that earlier port containers should not be buried under later port ones, and the assumption is that all containers are destined for one out of a number of ports, and unloading is purely by stack order, that is last in first out, right? So we employ this assumption, and reality is that some ports allow horizontal shifting or restacking on queue, which has been ignored here. For example, there are cases in which containers are loaded in this format on a ship, right? So let me draw and show you. For example, if we have containers loaded in this format, right? So these are all container. So if we remove, let us say, any of the container that we had from between, also the containers above that would be stabilized, right, by the left and right containers of a particular container, right? So even if I remove this, since this is being balanced, this can easily be removed without popping the container above this one out, right? So we have assumed that we can only have a vertical stack with all the dimensions equal. So that is why we are using this destination encoding assumption. Then the yard representation. So containers start at xy position in the yard plane. Uh, Now the loading cost is Euclidean distance from yard point to ship stack position. Assumption is that a single crane would pick the containers that are present in a yard directly with no queuing, no interference or any scheduling conflicts. So let us say this is the ship, right? We are just considering the coordinate of the ship and the coordinate in the yard where the container is present in a 2D coordinate axis, and we just need to bring it using a crane, and we'll consider only the Euclidean distance. So that is the assumption, where a single crane is picking containers with no queuing, no interference, no scheduling conflicts. But in reality, real cranes have limited reach, scheduling, and interference, right? There could be a terrain difficulty in terrain, so the crane would basically take a different path, so that would increase the path length. So we are not considering all those factors. Then the next is constraints. So rehandles and imbalance are modeled as penalties in the cost function, not as absolute prohibitions. The assumption here is that trade-offs are allowed. Sometimes small imbalance is acceptable for much shorter loading distance. In reality, some constraints like maximum allowable imbalance would be hard safety limits in practice. And next assumption is that container homogeneity. So containers differ only in weight, destination, and yard location is what we have considered. But the assumption here is that I've ignored hazardous goods and different container sizes and types. I'm basically considering homogeneous types of containers. That is, they have the same length, the same width, and the same height, right? In reality, there is dangerous good segregation and difference in dimensions and their types, etc. Right? That is the assumption. And our final assumption is that containers are placed in a fixed order. That is, they have been sorted by destination. Assumption here is that order of placement does not affect feasibility, only the cost. But in reality, we have dynamic placement order, which matters when we are searching for a global optimum. Now, moving on to our next slide. So how we are representing our input and objective function I'll cover in the next slide. So in input, basically, it is represented as a JSON format with containers and stacks. First, we have the assumptions. That is, the destination order is for one, it is the earlier port, and larger ports, if we keep on increasing the value to n, let us say we have n ports. So the destination n would come later and at the last, and one would be coming the first, right? So ideal stack order also is non-increasing bottom top. Then we have balance, which is the penalty on absolute difference between the right and left sides of the weights of the ship. So basically, that is the Euclidean distance that we consider. That is the container which is present in the yard, and the distance between container present in the yard and the stack present on the ship. So that is the distance we will be considering for the load cost. And then we have the rehandle cost. That is 3 per blocking inversion within a stack. Right. Now talking about the stacks. So we have stacks with the name of the container, sorry, name of the stack. That is L1, which denotes the side as well as the unique ID. And the side it is present in the ship, whether it is present on the left side or the right side. So we have stacks in this order, and then we have the position on which ship's position in the 2D coordinate axis of the ship. Where exactly is it positioned? So 10, 0, and the height limit of each stack. And then we have the containers. So the ID of the container, unique ID for container, the weight of that container, 12 tons, the destination, and destination basically the port number at which it has to be dropped off, and the yard position, the position in the yard at which the container is initially present. From that position, the crane will take it to the ship. Moving on to our objective function. So basically, this is the objective function. That is, the total cost is distance plus the rehandle penalty plus the balance penalty, and the distance cost is Euclidean yard to ship travel distance, which I discussed. And we have the rehandle penalty, in which we have 3 times the number of blocking inversions. So 3 is just an arbitrary number that I have chosen, and basically that is actually the distance weight lambda r, which I'm considering. Then the balance penalty is 0.1, again arbitrary number which we have chosen. We can change this as well. Times the absolute difference between left and right weights of the ship, and we have to calculate the trade-off between the efficiency and constraints. So this is our objective function. Total cost is equal to travel summation distance between the yard position and the ship position. That is the loading cost. Distance is Euclidean here, plus the inversion or the rehandle cost with the lambda r distance, rehandle weight, plus lambda b, which is the balance weight, times the absolute difference between left and right weights of the ship. So Now talking about what exactly the rehandle cost is. So that is summation of inversion of S. So that is basically the number of inversions or rehandles for the stack S. That is pairs of containers I comma j with I below j in stack, but the destination of I is less than destination of j. So what this means, I'll show you. Let us say we have containers in a stack in this format, and let us say this is ith container and this is the jth container. So basically, what an inversion would be is that these are pairs of containers I comma j with I below j. So you can see in the stack, I is below j vertically, right? In this case, in the stack, but the destination of I, let us say this has to be dropped off at destination 2, and j has to be dropped off at destination 4, or let us say 5, right? So this would mean that I has to be dropped off first. That means I has to be dropped off at an earlier port than j. So we have to basically unload these containers from the stack and then drop off I at the port number 2, and then also load the j, all these containers back above I, since they do not have to be dropped off earlier. And then because later on j would be dropped, but I has to be dropped off first. So this is actually the cost that is required to take out all the containers. That is the number of inversions or the rehandle cost. Since an earlier destination container below a later destination one in a stack causes a blocking. So that is why this is the inversion cost, which we have summed up for all the stacks. As you can see, summation, all the stacks are present in this stack set, right? So we are summing up all the stack, all those number of inversions for each stack, and lambda r is basically the value 3 that we have chosen here, which is the rehandle weight. And similarly, we have the lambda b, which is the balance weight. Now moving on, the algorithm choice. So basically, for the algorithm, I have used A star search with the beam pruning. A star basically ensures that the search is guided by a cost function fn is equal to gn plus hn, where gn is actually the cost that has been accumulated so far in actuality. So we have this as the actual cost accumulated so far, that is distance plus penalties, and hn is basically the heuristic lower bound, or you could say the this is basically the minimal extra distance to place remaining containers. So this is basically an educated guess using the heuristic that I have set to calculate the remaining cost. And beam search basically prunes the frontier to the top k nodes at each depth. So basically we are able to mitigate the exponential explosion. And it has heuristic design, that is we have admissible lower bound for remaining low distance, where we ignore the capacity, the number of blockings or the rehandles, or you could say the inversions, and also the balance. So it is optimistic. So here I would be placing the containers one by one, and this allows us to assign the containers to each stack quickly and lets us compute g incrementally. Now talking about the heuristic. So if I zoom in here, this is the heuristic that I set. HR, h distance of R is summation c belonging to R, minimum of distance between the yard position and the ship position, where R is actually the set of remaining containers that have not yet been placed on their way, right? Set of remaining containers not yet placed, and we are only considering the distance or the Euclidean distance between yard position and the ship position. So that is the heuristic. Set of remaining containers that have not yet been placed means that those containers which are still in the yard and are yet to be placed onto the ship stack, right? So that is the heuristic, and S is actually the set of ship stacks, right? So basically, the true minimal additional cost to place the remaining containers are includes at least the minimal transport distance for each container from the yard to the ship stack, and the additional non-negative penalties that we have, that is the number of rehandles or inversions, and also the balance cost of the ship that I have considered. So basically, this means that since edge distance is excluding those non-negative penalties, number of rehandles, and the balance cost, edge distance would be less than equal to the true minimal remaining cost. So that means H is admissible and it never overestimates, right? So that is why this is an admissible heuristic, and that is about the algorithm choice. Now going over to data structures and implementation. So basically, talking about the data structures, we have the container data class, which basically encapsulates all the essential attributes that we need for a container. That is its unique ID, the weight, the container's weight, the destination it has to be dropped off at, and the yard position it is initially present at. And also I have the ship stack data class, which has modeled a real world stack that is present on the ship. So it basically tracks the name of this stack, the side at which it is present, whether it's the left side or the right side, the ship position, the position at which like the coordinates at which it is in the ship, and the height limit, that is the maximum stack height that we can have, and also the slot configuration. Basically the slots are the ordered list to place the containers into the stack. Then we have the instance wrapper, which basically unifies the containers and the stacks, and basically these are present as dictionaries, and also has integrated the helper cost functions that we have. Now talking about the helper functions, we have the per stack blockings, that takes a stack as the parameter. So basically it measures how many rehandles or inversions are required when we are unloading the containers to reach an earlier destination, and this basically takes O of h square time. But since h, which is the height, is small, that is only height of the stack less than equal to 4 to 8, so basically it would not be a very costly function. Then we have the left right weights, which computes the imbalance between the left and right sides and is essential for the stability of the ship. So it takes O of number of placed containers time, right? So when we are placing the containers from the yard to the ship, let us say this is the ship and this is the container, we basically have to maintain the left right weights, number of placed. So that is why number of placed containers onto the ship would determine the stability of the ship, whether it is towards the left or the right. And we have the threshold set, right? Now, evaluate state is another function that we have, which basically computes the total cost of a state, that is the distance cost, along with the rehandle penalty and also the balance penalty. And here the distance cost is actually the yard to ship distance, which has been approximated as the Euclidean distance between the container's yard position and the position of the stack on the ship. Now, moving on, we have the node structure that is going to be helpful in our A star beam search, where we have state G, H, F. So state basically is configuration of stacks which containers are placed where. Then G tells us about the actual accumulated cost, which is the distance that has been moved, the number of rehandles, and the imbalance till now. H is basically the heuristic estimate of the future cost, or you could say the educated guess for the future cost that we'll be having in our algorithm. And F is basically G plus H, which is the standard function which we use for evaluation in A star search. Then we have the beam width and time limit, which are tunable parameters exposing the trade-offs between runtime and memory and the solution quality. And we have the files or the command line interface, which basically the files we have mainly the main.py. I have main.py, and the commands that I run is basically firstly in order to generate sample JSON, which I showed you in the input representation, we will use the sample function here, Python main.py sample, and the output directory is outputs. Then if we want to basically run the whole function of A star beam search, then we call the run function, and in output directory outputs we save it, and sizes of containers are mentioned here. Then we have the beam width 200 and the time limit as 30. So we basically use different we have created different combinations. So first we'll be considering number of containers as 12, then n is equal to 20, then 30, and then 35. And this basically what it does is it increases the beam width to 200 and the time limit to 30 seconds. We can also decrease it like 100 and time limit as 15, right? And I talk more about this in the results, how it's changing. And then for basically the next one, the third command that we have is Python main.py, which is the main function I have used here, and we call experiment function. In output directory, we store experiments, and we are basically using this function. We iterate over all the possible combinations of parameters. So I have basically created a parameter grid in which all possible combinations are tried out and stored in in a CSV file that I have in my code. So it basically tries out all the possible sizes like we did here, 12, 20, 30, and 35, and all possible beam widths. We can have 50, 100, 200 as well, right? All possible beam widths. Then time limit, all possible combinations like 5, 10, 30, 50 as well. Then order, that is the stacking order of the ship stack, right? Which order we'll follow. Then per side. So on the ship, per side, how many stacks we want to be present. So if we have 3 stacks per side, then that means we will have total of 6 stacks on the ship. If we have 4 stacks per side, then we have basically total 8 stacks per ship. And the height limit, we can increase the height from 3 to 4 height limit of each of the stacks, right? So all of these possible combinations I have basically set up in the parameter grid, and it basically repeats each run for the seeds that we have 1, 2, and 3, right? And as the output, we get our text logs, the CSV files having the metrics for the runtime, the memory in megabytes used, the cost, and basically the components of the cost, that is the rehandle cost, the distance cost, as well as the balance cost. So this is basically our implementation. Now moving on to results and analysis. So for very small instances n less than equal to 8, the runtime stays below 1.5 seconds. At n is equal to 11 and 12, runtime goes between 3 to 5 seconds, which is practical. And this is a run that I've shown for beam width that I've chosen as 200, and the time limit I've chosen as 30 seconds, right? So at n is equal to 20, runtime jumps to 24 seconds, showing near exponential growth. At n is equal to 30 and 35, the solver exceeds 30-second limit, which means that the output is incomplete since we have gotten a time limit exceeded clearly. So this confirms that the architecture does not scale well beyond 30 containers, especially at high beam width. So I've chosen high beam width to 200, right? That is the example that I've run it for. And now the impact of heuristics. So across all the tested instances, the rehandles that we have is 0. So heuristic successfully enforces destination order constraint. So basically, we have rehandles, or the number of inversions would be 0. That means any container that has to be dropped off first is actually placed at the more towards the top, and any container which has to be dropped off later on has been closer to the bottom. Now the balance penalty was also always bounded. That is, the difference between the left and right weights is less than equal to 33, which I saw in my run, meaning no dangerous load skew. That is, the ship would be balanced because this is the threshold that I've set. And distances optimized fairly well. Total cost stays within a reasonable range. That is 30 to 75. The cost was total cost for n less than equal to 12. Heuristic thus provides strong pruning, which focuses the search on feasible and low rehandle states, and also prevents the wasted exploration of infeasible stacking. So heuristics here is basically not just guiding the search, but also actively pruning the infeasible or the dangerous states, making our solutions faster as well as safer. Now talking about the quality of solutions. So the cost grows moderately with size up to n is equal to 12. That is from 30 to 76, this range. At n is equal to 20, the cost has jumped to 155.7, reflecting both higher transport effort and the beam search pruning effects. Quality remains good. Rehandle penalty has never been triggered, right? And balance always within the safe bounds. And also runtime cost dominates for larger n. Now beam width and time limit effects. So I've chosen beam width as 200. It ensures a strong exploration of all the possible states that we have. Then trade-off, high runtime cost, especially beyond 12 containers. Time limit 30 seconds acts as a safety cutoff. We can also decrease the time limit for our algorithm, that is the A star beam search, to run for a lesser time, right? And at n is equal to 30 and 35, the algorithm stops mid search. No final cost is obtained. So that's it about the presentation.